Hi. One of the things I think you all need to do is sort out reactions that involve halogen. I also think you need to sort out the reactions that involve making alcohols. So you've got to start thinking about what you're making and not just about the mechanism of the reaction, which is a great thing to think about. Okay? One of the things that really confuses people is that there are a lot of reactions that involve halogens, and they get them mixed up, and they start confusing the reagents. So these are the reactions that involve halogen, and you need to learn them. The simplest and most fundamental reaction is taking some kind of alkane, adding a halogen in the presence of light to form a substituted alkane. And as I told you, this is a great method of activating an alkane. Now recently, we have expanded this reaction to include allylic and benzylic sites. So you can take these reagents and you could have an aromatic system such as this, and if you added X2 in the presence of light, you would obtain, I'm turning this around and I hope, are you getting a good picture of this? Mm-hmm. You would obtain that compound. On the other hand, if you have some kind of allylic system, and you add X2 in the presence of light, it's a little problematic. And the reason it's a little problematic is that if you have a high concentration of X2, you can get some addition across the double bond. But under these conditions, you should get at least some allylic, let me take one of these out, some allylic bromination. So your products would look like this, and you really wouldn't differentiate between the products in terms of yield, although they would not be formed in equal yield. So you would obtain that product and this, which would come from the other resonance form. This is what we've been talking about in class. I am kind of hung up on bromine, and I will use bromine in a lot of my examples. So you would get this as well. The reason being that you form the free radical halide. The halide pulls the tertiary allylic hydrogen off to form the tertiary allylic radical, and the tertiary allylic radical has more than one resonance form, the other resonance form being this. And this, again, has been what we have been working on in class recently, is the idea of adding resonance into our normal daily reactions. Okay, what else have we got? Well, these are all the same thing. What I recently introduced to you in class is the idea that instead of using, say I had the same substrate, instead of using bromine, you could use a reagent called NBS, which I described in class, in the presence of light. Under these conditions, you would obtain the same products, and as I described in class, this is really a bromine factory. If there's any HBr around, you will produce bromine. This was covered in class. Okay, so you would get those products. This is a better way to do it because this produces small amounts of bromine over time. And in low concentrations of bromine, you have a less likely chance that the bromine will add across the double bond. Plus, it's an easier reagent to work with, but it is a source of radicals, and rather, it's a source of Br2. It's kind of like a slow source, so it's produced kind of in situ. Okay, now, what I just, oh my gosh, oh dear. Well, all right. Yeah, I'm all right. We got a little excitement there. Okay, can you still see this? Mm-hmm. All right. Yes, the board almost fell down. Okay. Anyway, those reactions are all the same thing. Okay? What are other reactions involving bromine? Other reactions involving bromine would be just the normal addition, let's make a ring, the normal addition of bromine across a double bond. Now notice there's no light here. You have to sort these things out. So you might do this, for example, in carbon tetrachloride. If you did this, you would obtain the anti-addition of bromine across the double bond. Okay? Bromine and light, different story. Bromine, this is what you get. Completely different reaction. If I took the same substrate and I add HBr, and only HBr, this does not work with HCl, in the presence of peroxides. Notice peroxides have to be there. A free radical initiator has to be there. And you can do this in light or even with a little heat. What will happen is you will obtain, oh, I should have made some regiochemistry here, so I'm putting a methyl in there. You would obtain, this is very useful synthetically, the anti-Markovnikov halide. Okay, there's stereochemistry there that I'm not including. However, right, if I take the same substrate, how much time do I have?
4 minutes.
Oh my goodness. So if I have the same substrate and I add HBr or HCl, I will obtain this. I want you to think about this mechanistically, why these are different. You know, what's different about these reactions, okay? Is there more with halides? Yes, there's more with halides. Okay, what else can you do with halides? There's even more. We will learn more as the week goes by. Okay. What did I forget? Okay. What did I forget? Oh yeah, I forgot this. So you can take a double bond and you can add X2 in the presence of water. And I'll give it some regiochemistry. Well, this one doesn't have such great regiochemistry. But you would obtain this. This is the halohydrin, and of course it's very important in making epoxides. Okay? What else? All right, so what have we added into the repertoire? What we have now added is the addition of HX across a conjugated system at low temperature and at high temperature. And what we discovered was at low temperature, which we called kinetic conditions, we obtained mainly the so-called 1,2 product, which is also kind of a proximal product, which we described in class. And then when we're at 80 degrees Celsius, you would get mainly what is called the thermodynamic product, or the one, it's not always the 1,4 product. But remember, at high temperature, it's equilibrating, and what matters most is the stability of the double bond. You can also do this reaction with X2. And that's the last thing I want to talk about. Maybe. Okay, so let me erase this. This is like a cram course in halogens. Oh, there's more. Wait a minute. Let me do this quickly. How much time do I have? I can go over a little bit.
2 minutes.
Okay. They actually accept my things if they're longer. But if you have this, plus, say, my favorite, I'll use my less favorite halogen, chlorine, you will get a combination of this plus this. Okay? What this is showing is that chlorination is just like the addition of HCl across a conjugated system. And it shows that the halonium ion is kind of trumped by the resonance because of this product forming. Now, if I'm at low temp, this would be my product. And if I was at high temp, we would predict that this is our product. What's going on mechanistically? What's going on mechanistically is the chlorine is adding kind of like a hydrogen. You probably can imagine when you have this plus here that there's some relationship there between the chlorine and the positive charge. And there probably is a little bit of interaction, but the resonance trumps it. So the resonance is more important than the halonium ion. So we have to draw this other resonance form. We actually get products from this distribution of charge. So this puts the positive charge on the end. So really, we really will see both of those products if we do that in the lab, which means the halonium ion has kind of gotten thrown out of the picture. It's not as important. Think about it. The cation's going to do whatever stabilizes it best. There are two things it can do. It can share with that chlorine or it can share across this whole system, and it's more stable for the charge to go through what we call the pi way than to just be shared with an adjacent chlorine. And that's generally true. And this is just with one pi bond. Okay, lastly, don't forget, okay, you can also make halides from alcohols and just other good leaving groups. So for example, if I have something like this, and I add HBr to it, these are reactions you should remember. You will obtain this, and a Br minus, okay? And you would obtain that product. So that's another way you can make halides. So we have all these different methods. One of the things that I think is interesting is that people frequently confuse their free radical reactions. And they really get confused between, like, why do we pluck the hydrogen there versus why do we attack the double bond? And I want you to think about this, like supposing I have HBr.
You're at 11 minutes.
Okay, and I have peroxides. Is it still running?
Mm-hmm.
Okay, if I had this and I heated it, right? You would go ROOR, split the peroxide in the light, or the heat, and you would get that radical, right? So then this radical, what it does, preferentially, is it pulls the hydrogen off the bromine, and it forms a bromine radical. And you might be tempted, you might say, why can't I just take that bromine radical and add it into the double bond, okay? But think of, or that's what you do, I'm sorry. But you might think, why don't I just pluck that H off? But think about this. If you pluck the H off, right, you'll get the resonance stabilized radical. Okay, you will get that. But what does it have to react with after that? It doesn't have Br2. Normally when you brominate here, you're in bromine, Br2. So what does it attack? If you formed any of this, it would just take the H off HBr and reform the bromine radical, and you'd just be back to where you started from. So I find with free radical reactions, a lot of times you can figure out why it goes the other way. Okay? So I'll see you in class tomorrow.